and today we're going to be looking at what is called arithmetic sequences. Sounds fancy and a little bit tricky, but I think you guys will get it. So linear functions are also arithmetic sequences. The input x represents the term of the number in the sequence, and the output y represents the number in the sequence that follow a pattern. An arithmetic sequence is a set of numbers that follow an addition or subtraction pattern. So consider the following. Here we have a table of values like the ones we've seen in the past where we have to find a function rule. In the above table, the first term is 19. The second is 23. The third is 27, and so on. This is an arithmetic pattern as 4 is being added each time in the second row. So we ignore the top row and we just look at the second row. If I add 4 to 19, I get 23. If I add 4 to 23, I get 27. If I add 4 to 27, I get 31. And if I add 4 to 31, I get 35, proving that this is an arithmetic sequence because of the addition pattern. So there are some formulas here that we need to know. All of these are very similar to the linear function rule y equals mx plus b, and I'll show you why in a little bit. So an explicit formula is a formula that can be used to find any term in the sequence or to determine what term a number in the sequence is. So again, these look a little tricky, but stay with me. I think you can get it. F of n equals d of n minus 1 plus f of 1. So we leave the n minus 1 and we just substitute in for the common difference in the first term. So d is what we're going to call the common difference, which was 4 in that example. And then f of 1 is just the first number, which was 19 in the example. Another way of writing this, instead of using an f with parentheses and n, is a of n. This a subscript n is still said a of n equals d again times n minus 1 plus a of 1. Again, the d is the common difference, and again, the a of 1 is the first term. Then a recursive formula is a formula that can be used to generate a sequence given the first term. So f of n equals f of n minus 1 plus d, where f of 1 equals the first term. So again, that f of n minus 1 is the previous term. We're not going to substitute it for anything. And d is the common difference. Again, a of n equals a of n minus 1 plus d, where a of 1 equals the first term. So the formulas look tricky, but as soon as we start using them, you will probably catch on. Using the above table, the formulas would be, so in the example, remember it was an adding 4 formula or an adding 4 pattern with the first term of 19. So the explicit equation would be f of n equals 4, which is the common difference, times n minus 1, plus 19, which is the first term. Now, if I were to go back from 19 and subtract 4, I would get 15, and that would be the 0 term. So this equation is actually equivalent to f of n equals 4n plus 15. It generates the exact same sequence. The only difference is here we start with the first term, and here we start with the initial or 0th term. Okay, so that's something to keep in mind, and you should be able to determine that those two equations are exactly the same. If I were to distribute this 4n, I would get 4n minus 4, and negative 4 plus 19 is the 15. Then the recursive formula is f of n equals f of n minus 1 plus 4, where the first term is 19. So if I plug in the 19 here, it replaces this whole thing, and I would do 19 plus 4, and I would get the second term, which is 23. And if I plug in the 23 there, I would do 23 plus 4, which gives me the third term of 27. And if I plug in the 27 there, I would get 27 plus 4, which is 31, which is the fourth term, and so on. So let's try some of these. In our first example, again, we don't really have to bother looking at the first row. We want to look at the second row and see what pattern we find. So 6 to 13 is increasing by 7. 13 to 20 also increasing by 7. 20 to 27 also increasing by 7. 27 to 34 also increasing by 7. So 7 is our common difference and 6 is our first term. So our explicit equation would be f of n equals 7 times n minus 1 plus 6. Now, if I went backwards 7 and I did 6 minus 7, I would get negative 1, and negative 1 would be my 0 term. So this is also equivalent to 7n minus 1. Again, if I were to distribute that 7, that would be my simplified equation. So they are equivalent, and you should be able to recognize that. And then my recursive equation, or formula, would be f of n equals f of n minus 1 plus 7, since I am consistently adding 7, where the first term is 6. And again, if I plugged in 6 and added 7, I'd get the second term, which is 13. If I plugged in 13 and added 7, I get the third term, which is 20, and so on. Now, number 2, your table might look different than mine, and if it does, fix it. I had to adjust some things. We look for a pattern again. 12 to 7 is subtracting 5. 7 to 2, also subtracting 5. 2 to negative 3, also subtracting 5. And negative 3 to negative 8, also subtracting 5. So that makes my common difference negative 5 and my first term 12. So we have explicitly f, or a of n this time, because that's the way the table is read, equals negative 5 times n minus 1 plus 12. And again, if I were to go back 5, add 5 to 12, I would get 17. So this would also be equal to negative 5n plus 17, where 17 would be the 0th term rather than the first term, or the initial term. Then recursively, we have a of n equals a of n minus 1 minus 5, where the first term is 12. Okay, so that's when you're looking at a table. Now, typically when we see this, we're not going to be looking at a table. We're just going to look at a sequence. Let's see some examples. So here we have number 1 is negative 8, negative 10, negative 12, and negative 14. So the first term is negative 8, the second term negative 10, the third negative 12, and the fourth is negative 14. Negative 8 to negative 10, we subtract 2. Negative 10 to negative 12, we also subtract 2. Negative 12 to negative 14, we also subtract 2. So that makes our common difference negative 2 and our first term negative 8. So explicitly, this is a of n or f of n. I'm going to go with f of n equals negative 2 times n minus 1 minus 8, because we're starting with negative 8 as our explicit formula. If we went back 2 more, we would get negative 6. So this would be equal to negative 2n minus 6. And if I plug in 1, negative 2 times 1 minus 6, that's negative 2 minus 6. There's our negative 8. So it generates the same sequence. Okay, and then we have our recursive formula, which is f of n equals f of n minus 1 minus 2, where the first term is negative 8. And again, that's just generating the sequence. If I plug in negative 8, I subtract 2, I get negative 10 for the second term. If I plug in negative 10 and subtract 2, I get negative 12. If I plug in negative 12 and subtract 2, I get negative 14, and so on. Okay, number 2, same idea. Again, we're looking for the pattern. So 9 to 15 is increasing by 6. 15 to 21 is increasing by 6. 21 to 27 also increasing by 6. And 27 to 33 also increasing by 6, making my common difference 6 and my first term 9. So explicitly, we could write a of n equals 6 times n minus 1 plus 9. And if I went back 6, a of n equals 6n plus 3, where 3 would be the initial amount rather than the first term. Then recursively, and let me just show you again, if I were to plug in, for example, 21 here, that's the third term. If I do 3 minus 1, I get 2. 2 times 6 is 12, and 12 plus 9 is 21. So it generates that term as well if I plug in the term number that is wanted. Now, recursively, this would be a of n equals a of n minus 1 plus 6, where the first term is 9. Okay, so We're going to continue using these types of sequences the next couple of days and really making sure that you understand the difference between what an explicit equation is and what a recursive equation is and what they're used for. So, giving those examples, you guys are now on your own. You're going to try questions or problems 3 through 8. Check in with me so I can be sure that you